We are now finally prepared to look at the theorem that will tell us how we should construct the A matrix in order to perform the desired transformation. So we're going to write it this way. We're going to define a transformation. For any transformation, call it T, and the colon just says, here's what it's starting with. Here are your input vectors. So our input vectors are in n dimensions, and our output vectors are going to be in m dimensions. So we're going to start with an n by 1 vector, and so we'll just kind of call those components x1 through xn. And then, so the transformation will take those and will produce m dimensional vectors, which we'll just refer to as b1 through bm. N and m could be the same thing, but they don't have to be. And as long as we know that our transformation is linear, then the following way will tell us how to construct the A matrix. So T of x equals AX, there's our function. Remember, we decided we're just going to call that a transformation. That A matrix is going to be this right here, this cryptic looking thing. And what this matrix will have in it is it will have as its columns the transformation of each of those n standard basis vectors in your input space. Okay, so let's think about this for a second. If we were to go from, let's say, R3 into R2, then we would have, in our case, n is equal to 3. And so we would have vectors E1 through E3. So let's go ahead and craft this out. We'll have E1, 1, 0, 0. We'll have E2, 0, 1, 0. And we'll have E3, which is 0, 0, 1. And so in order to construct the A matrix, what we have to do is we have to transform the 1, 0, 0 vector, and how we do that depends on what the transformation does. So if it rotates that vector 30 degrees, then we have to rotate the vector 30 degrees. And so we have to transform each one of these according to the instructions of the transformation. We'll take a look at more concrete examples soon. And once we have those three things, what we're going to do, now remember, each of these is going to produce a new output, and we're transforming vectors in n dimensions into vectors in m dimensions. So this vector that we get as an output will have two components, and I'm just going to do dots in there because I don't know what those two components are going to be. It depends on what you're doing to that vector, what kind of transformation. But the point is, this will produce 3 2 by 1 vectors. And okay, so in this first column in the A matrix, what we have to place in here is the transformation of E1. Okay, and that's going to be a column. That result is a column. It's a 2 by 1 column. And then the second column, we're not adding these together. We're just transforming each of the columns and creating out of them new columns. And then the third column in this matrix, in this example, will be the transformed 0, 0, 1 vector. And so if that's all too much to take in, well then at the end of the day, you'll just have each of the 2 by 1 vectors, right? Each of these three guys will be the, here we'll have, let's do this one in green here. That's going to be this column. This one I'll do in orange. That's going to be the second column. And it does have to go in order of E1 all the way up to E3. You cannot reverse these. It does mess with the matrix. And there is our matrix. Now, if you notice, it has 3 columns and 2 rows. So this is a 2 by 3 matrix, which we already said A is an m by n matrix. Okay, A is m by n, and so in our case m was 2, n is 3. So the beauty of this is you don't have to worry about the final dimension of A. All you have to worry about is list out the standard basis vectors in the input dimension, transform each one of them into the m dimension, and then take each of those resulting vectors and place them as in order as your columns of the A matrix. And as long as the transformation is linear, the A matrix that you construct will always perform that operation on any vector that you multiply it by.